In a secret military factory deep in China's interior, engineers stared in horror as their prototype machine gun tore itself apart during its first live-fire test. Metal shards flew through the air. The barrel glowed red-hot before warping like melted wax. 7 years of work destroyed in seconds. But this catastrophic failure would become the beginning of one of the most dramatic stories in modern weapons development. This is the story of how China tried to copy America's legendary M60 machine gun, and how everything that could go wrong did go wrong.
The shadow of war. The year was 1976, and China faced a crisis that few outsiders understood. While the world watched the end of the Cultural Revolution and the death of Chairman Mao, military commanders in Beijing confronted a terrifying reality. Their armed forces were equipped with weapons technology that was, in some cases, decades behind their potential adversaries. In the dimly lit conference rooms of the People's Liberation Army headquarters, senior officers reviewed intelligence reports with growing alarm. The Type 56 machine gun, China's standard squad automatic weapon, was showing its age. Based on the Soviet RP-46 design, itself derived from the World War II-era Degtyaryov machine gun, it was heavy, cumbersome, and increasingly unreliable in field conditions. But it was the reports from Vietnam that truly alarmed Chinese military planners. During the Vietnam War, American forces had deployed the M60 machine gun with devastating effectiveness. Chinese military observers, working alongside North Vietnamese forces, had witnessed the weapon's capabilities firsthand. The M60 could sustain fire rates of 550 rounds per minute. It was relatively lightweight at 23 pounds. It could be operated by a single soldier if necessary, and most impressively, it demonstrated remarkable reliability in the brutal jungle environment where other weapons failed. Lieutenant Colonel Chen Wei, a firearms engineer at Factory 208, one of China's premier weapons development facilities, remembered the moment he first held a captured M60. It was like holding the future, he would later recall in declassified interviews. The Americans had created something that changed the nature of infantry combat, and we had nothing that could match it. The decision was made at the highest levels of the Chinese military. China would develop its own general-purpose machine gun, and the M60 would serve as the foundation. It seemed like a straightforward task. After all, China had successfully reverse-engineered Soviet weapons for decades. How difficult could one American machine gun be? They were about to find out.
The optimism of ignorance. The project began in late 1976 with infectious enthusiasm. Factory 208, located in the mountains of Sichuan Province, was assigned the task. The facility had a proud history. It had successfully produced Chinese versions of Soviet small arms and had a staff of talented engineers and machinists. The project director, Senior Engineer Liu Zhenghua, assembled his team with confidence. They had acquired several M60 machine guns through various channels, some captured in Vietnam, others obtained through third parties. The weapons were meticulously disassembled, measured, photographed, and analyzed. We treated each component like an archaeological treasure, recalled Zhang Ming, a junior engineer on the project. Every screw, every spring, every surface was documented. We used calipers, micrometers, every measuring tool we had. We created detailed technical drawings of every part. The M60's design was elegant in its complexity. At its heart was a gas-operated firing mechanism that used the pressure from fired rounds to cycle the action. The bolt system was a marvel of engineering, a rotating bolt that locked into the barrel extension with multiple lugs, distributing the enormous pressures generated during firing. The feed system used a clever design that could accept ammunition from belts on either side of the weapon. The Chinese engineers believed they understood it completely. Their drawings filled hundreds of pages. They calculated the metallurgical requirements for each component. They designed manufacturing processes. They set ambitious timelines. The first prototype would be ready, they estimated, within 18 months. It would actually take 6 years to produce a weapon that didn't immediately self-destruct. And even that wouldn't work properly.
The devil in the details. The problems began almost immediately, though the team didn't realize it at first. The first challenge was materials. The M60 was manufactured using specific steel alloys developed by American metallurgists. These alloys had precise chemical compositions and heat treatment requirements that gave them the exact combination of hardness, toughness, and heat resistance needed for sustained automatic fire. China's steel industry in the late 1970s, while impressive in scale, lacked the sophisticated quality control systems of Western manufacturers. The team at Factory 208 specified steel grades that seemed equivalent on paper, but metallurgy is an art as much as a science. Tiny variations in carbon content, trace elements, or heat treatment could dramatically alter a metal's properties under stress. "We tested our steel samples in the laboratory," Zhang Meng explained. "They met the hardness specifications, they showed good tensile strength, but laboratory tests don't replicate the reality of sustained automatic fire, where metal is subjected to thousands of rapid heating and cooling cycles, enormous pressures, and complex vibrational stresses." The second challenge was manufacturing precision. The M60's components were machined to tolerances measured in thousandths of an inch. In American factories, this was achieved using advanced machine tools with numerical control systems and rigorous quality inspection procedures. Factory 208's machine tools were good, some of the best in China, but they were primarily designed for producing larger components. Achieving the required precision for the intricate parts of an automatic weapon pushed them to their limits. More critically, maintaining that precision across hundreds of parts, each made by different machinists on different shifts, proved nearly impossible with the quality control systems available. The third challenge, and this would prove the most insidious, was something the engineers never anticipated: the problem of silent knowledge. What the drawings couldn't capture. In late 1978, after 2 years of preparation, Factory 208 was ready to assemble its first prototype. The components had been manufactured according to the detailed specifications. The parts fit together, mostly. Some required hand fitting and adjustment, but this was expected in prototype work. The moment of truth came on a cold morning in January 1979. The prototype, designated Type 80, the name was optimistically chosen to indicate an expected service entry date of 1980, was mounted on a test stand in Factory 208's indoor firing range. Engineers and military observers crowded behind protective barriers. Colonel Liu himself would fire the first burst. He chambered a round, aimed downrange, and squeezed the trigger. The weapon fired 3 rounds, then it jammed. This wasn't entirely unexpected in a first prototype. The team cleared the jam, made some adjustments, and tried again. This time, the weapon fired a dozen rounds before the bolt carrier group seized completely, the gun freezing mid-cycle. Over the following weeks, the prototype was repeatedly modified, adjusted, and tested. Sometimes it would fire a full belt of ammunition without incident. Other times it would jam after just a few rounds. The behavior seemed almost random, which was perhaps the most frustrating aspect. Then came the catastrophic test. During an extended firing session designed to test heat tolerance, the prototype was fired in sustained bursts simulating combat conditions. After approximately 400 rounds, witnesses heard an ominous change in the weapon's sound, a higher-pitched whine mixed with the usual staccato of gunfire. Before anyone could react, there was a sharp crack. The bolt had sheared in half. The rear portion remained locked in the receiver, while the front portion, still attached to the firing pin, was propelled backward by the pressure of the cartridge. The bolt carrier group disintegrated. Metal fragments punched through the receiver cover. If Colonel Yu hadn't been wearing protective eyewear, he would likely have been blinded. The test was immediately halted. The prototype was tagged for failure analysis. Engineers carefully examined the broken bolt under magnification. What they found was deeply troubling. The fracture surface showed signs of metal fatigue, tiny cracks that had propagated through the bolt over hundreds of firing cycles before the final catastrophic failure. But more concerning was the pattern of wear on the bolt's locking lugs. They showed uneven contact with the barrel extension, indicating that the forces during firing weren't being distributed properly. This led to a disturbing realization. Their measurements and drawings, as detailed as they were, had missed something crucial.
The invisible knowledge. The problem the engineers eventually understood was that a mechanical drawing cannot capture everything necessary to manufacture a complex machine. Consider something as seemingly simple as the surface finish on the bolt's locking lugs. The drawing specified a smoothness level measured in micro-inches. The Chinese machinists achieved this specification. But what the drawings couldn't convey were the subtle variations in how American machinists approached this task. The specific grinding wheel grades they used, the speeds and feeds, the finishing techniques that created not just a smooth surface, but one with specific microscopic characteristics that affected how the metal wore under stress. Or consider the heat treatment of the barrel. The specifications called for the steel to be heated to a specific temperature, held for a specific time, then quenched. Simple, right? But the American process involved dozens of subtle factors: the exact atmosphere in the furnace, the uniformity of heating, the quenching medium's temperature and agitation, the subsequent tempering process. Each factor could alter the final metallurgical structure in ways that weren't apparent until the component was subjected to the extreme stresses of sustained automatic fire. These were examples of what engineers call tacit knowledge, the kind of understanding that exists in the hands and minds of experienced craftsmen, but can't easily be written down. When American machinists at Sacco Defense, the M60's manufacturer, made a barrel or bolt, they weren't just following specifications, they were applying generations of accumulated manufacturing wisdom. Factory 208's machinists were skilled, but they didn't have this specific accumulated wisdom. They were trying to learn in months what American manufacturers had refined over decades. We had copied the design, Zhang Meng reflected years later, but we hadn't copied the knowledge of how to build it.
Back to the drawing board. The catastrophic failure of the first prototype forced a complete reassessment. A second prototype, already under construction, was put on hold while engineers redesigned the bolt assembly using stronger Chinese steel alloys and modified geometries to account for the uneven stress distribution they'd discovered. This led to a cascade of changes. Strengthening the bolt required modifications to the bolt carrier. Those modifications changed the timing of the gas system. Adjusting the gas system affected the cyclic rate. Altering the cyclic rate impacted the feeding mechanism. Each change rippled through the design. By 1980, Factory 208 had produced 3 more prototypes, each incorporating lessons from the previous failures. None performed satisfactorily. The weapons were plagued by different problems: failure to extract spent cartridges, premature wear of the gas piston, breakage of the feed mechanism,
and in one spectacular case, a runaway gun that continued firing after the trigger was released until the ammunition was exhausted. Military observers, initially enthusiastic, grew increasingly skeptical. The project was consuming resources that could be allocated elsewhere. Other nations were developing new machine gun designs. The M60 itself, by 1980, was showing its age. American forces were already discussing replacements. Was the project worth continuing?
The stubborn refusal to quit. Colonel Yu faced a critical decision in late 1980. The rational choice might have been to abandon the M60 copy and pursue an original design, or perhaps try to license produce a foreign weapon. But Liu was a stubborn man, and he had become personally invested in solving this puzzle. "We have learned too much to quit now," he argued to military leadership. "Every failure has taught us something. We understand the problems now. Give us more time." He was granted 2 more years. The team's approach shifted. Rather than slavishly copying every detail of the M60, they began to adapt the design to work with Chinese manufacturing capabilities and materials. It was a delicate balance. Change too much, and you might introduce new problems. Change too little, and you'd repeat old failures. They redesigned the bolt with more robust locking lugs and a different heat treatment process better suited to Chinese metallurgy. They modified the gas system to be more tolerant of variations in ammunition quality. Chinese cartridge production also suffered from consistency issues. They added reinforcement to stress points identified in previous failures. The 4th major prototype, completed in early 1981, showed promise. During initial testing, it fired 2,000 rounds with only minor stoppages. Engineers cautiously allowed themselves to feel hopeful. Then came the endurance testing. Military specifications required that a general-purpose machine gun survive firing 10,000 rounds in various conditions with minimal maintenance. The M60, for all its flaws, and American soldiers had plenty of complaints about it, could meet this standard. The Chinese prototype began its endurance test on a humid summer morning. For the first 3,000 rounds, it performed adequately. Engineers monitoring the test noted some heating issues and increased wear on certain components, but nothing alarming. Then, around the 4,000 round mark, accuracy began to degrade noticeably. By 5,000 rounds, the headspace, the critical gap between the bolt face and the chamber, had increased beyond acceptable limits, a sign the components were wearing or deforming. At approximately 6,200 rounds, the barrel's rifling began to show significant erosion. At 7,400 rounds, the extractor broke, causing persistent failures to extract. The test was terminated at 8,000 rounds when the gas tube cracked, venting propellant gases into the receiver and making the weapon unsafe to fire. The prototype had failed to meet the minimum endurance requirement.
Understanding the gulf. The failure of the endurance test was particularly disheartening because it revealed just how far Factory 208 still was from achieving their goal. The problems weren't dramatic explosions or catastrophic breakages anymore. They were the slower, grinding failures of components that couldn't withstand sustained use. This pointed to fundamental issues in materials science and quality control that couldn't be solved simply by modifying the design. Consider the barrel erosion problem. When a gun fires, the barrel is subjected to temperatures exceeding 2,000 degrees Fahrenheit and pressures over 50,000 pounds per square inch thousands of times in rapid succession. The rifling, the spiral grooves cut into the barrel's interior, must maintain its dimensions under these conditions. If the steel isn't properly formulated and heat-treated, the rifling will gradually wear away, destroying accuracy. American barrel manufacturers had spent decades developing steels and surface treatments specifically for this application. Some of this knowledge was documented, but much of it was proprietary or existed only as trade secrets and manufacturing know-how.
China in 1981 simply didn't have equivalent capabilities. The nation's steel industry could produce large quantities of material for construction, shipbuilding, and heavy machinery, but specialty steels for demanding applications, jet engine components, precision bearings, gun barrels, remained a weakness. Factory 208's engineers found themselves fighting on two fronts. Not only did they need to perfect the design of the weapon, but they also needed to advance China's metallurgical capabilities just to manufacture the components properly.
The pressure mounts. By 1982, the project was in crisis. 6 years had passed since its inception. Millions of yuan had been spent. 5 major prototypes had been built, each showing some improvement over its predecessors, but none meeting military requirements. Rumors circulated through Factory 208 that the project would be canceled. Some team members were quietly reassigned. Budget allocations were reduced. The sense of urgency and excitement that had characterized the project's early days had been replaced by a grinding sense of futility. Colonel Yu, now older and worn down by years of frustration, faced his own crisis of confidence. In quiet moments he questioned whether the entire approach had been misguided from the start. Perhaps trying to copy the M60, a weapon designed around American manufacturing capabilities and material science, was fundamentally the wrong strategy for China. Yet he couldn't bring himself to abandon the project. The team had accumulated so much knowledge, learned so many lessons. They understood the weapon's operation at a level far deeper than when they'd started. They had developed new manufacturing techniques, improved their metallurgical processes, and trained a generation of engineers in the complexities of automatic weapons design. Surely that knowledge had value. Surely they were close to a breakthrough. In fact, they were about to receive an unexpected lifeline from an unlikely source.
The unexpected discovery. In the summer of 1982, a junior engineer named Wang Feng made a discovery while examining one of the captured M60s. Not the weapon itself, but documentation that had been overlooked for years. Among the materials acquired with the captured weapons were several technical manuals, standard U.S. military publications for armorers and maintenance personnel. These had been cursorily examined early in the project, but dismissed as basic operational information of little value to engineers trying to understand the weapon's design. Wang, unable to sleep one night after another frustrating day of testing, began reading through these manuals more carefully. What he found was a revelation. The manuals didn't just describe how to operate the weapon, they described common failure modes, wear patterns, maintenance procedures, and, crucially, what variations from specifications were acceptable. They contained tolerances for worn components, describing at what point various parts needed replacement. This information was a goldmine because it revealed something the engineering drawings never could: what aspects of the design were critical and what aspects had more flexibility. It showed which dimensions absolutely had to be maintained and which could vary without affecting reliability. It provided insights into how the weapon actually performed in field conditions rather than on paper. It was like finding the teacher's answer key after spending years trying to solve impossible mathematics problems, Wang later wrote. Suddenly, we understood not just what the design was, but why it was that way. Armed with this new understanding, the team began yet another redesign. But this time, they approached it differently.
The final push. Instead of trying to replicate the M60 exactly, the team now focused on understanding the principles behind each design choice, and then implementing those principles in ways compatible with Chinese manufacturing capabilities. For example, the barrel problem was addressed not by trying to perfectly replicate American barrel steel, but by redesigning the barrel profile to better dissipate heat,
and developing a different chrome plating process for the bore that Chinese manufacturers could reliably reproduce. The result was a barrel that, while different in some details from the M60s, achieved similar durability through an alternative approach. The bolt assembly was redesigned with larger locking lugs and different surface treatments that better suited available Chinese metallurgy. The gas system was modified with a regulator that could be adjusted to compensate for variations in ammunition, turning a weakness, inconsistent cartridge production, into a design feature that increased reliability. Throughout late 1982 and early 1983, a sixth major prototype took shape. The weapon that emerged looked similar to the M60, but incorporated dozens of modifications born from years of hard-won experience. The final test came in March 1983. Military observers, skeptical after so many previous failures, nevertheless assembled to witness the endurance testing of Prototype 6. The weapon was loaded. The first burst was fired. Then another. And another. The test continued through the day. 1,000 rounds. 2,000. 5,000. Engineers monitoring the weapon noted that temperatures and wear patterns were within acceptable ranges. The mechanism cycled smoothly. Feeding was reliable. At 10,000 rounds, the test was paused for inspection. The weapon showed wear, certainly, but all components remained within specifications. Accuracy had degraded slightly, but remained acceptable. The test continued. 15,000 rounds, 20,000. At 25,000 rounds, the test was finally concluded, not because the weapon failed, but because it had far exceeded the minimum requirements, and there was no need to continue. Prototype 6 had succeeded.
Reflections on the journey. The weapon that eventually entered limited production as the Type 80 machine gun was, ironically, no longer a copy of the M60. Through years of iterative failure and redesign, it had evolved into something different, a weapon that embodied M60 design principles but was thoroughly adapted to Chinese industrial capabilities and military needs. It was never produced in large numbers. By the time it was ready, military requirements had evolved, and the PLA was already looking toward next-generation weapons. But the Type 80's significance wasn't in its deployment numbers. It was in what its development taught Chinese defense industries. The project demonstrated that reverse engineering complex systems wasn't simply a matter of measurement and replication. It required understanding not just what something was, but why it was that way, and how to achieve the same functional goals using different means when necessary. It revealed the critical importance of manufacturing capabilities and quality control in weapons production. It showed that tacit knowledge, the unwritten understanding that experienced manufacturers possess, could be as important as formal specifications. These lessons would inform Chinese weapons development for decades to come. For the individuals involved, the project left mixed legacies. Colonel Liu retired shortly after the Type 80's successful testing, his health damaged by years of stress, but his reputation intact. Several engineers from the project went on to lead other weapons development programs, applying lessons learned from those frustrating years. Zhang Ming became a senior consultant, mentor to a new generation of engineers. Wang Feng, whose late-night reading of maintenance manuals had provided a crucial breakthrough, reflected years later on what the experience had taught him. We began this project thinking engineering was about precision, exact measurements, perfect replication. We ended it understanding that engineering is about problem solving, about finding ways to achieve objectives even when the path you expected doesn't work.
The M60 taught us as much through what we couldn't copy as through what we could.
The broader lesson. The story of China's attempt to copy the M60 machine gun is, in many ways, a microcosm of a larger story about technology transfer, industrial development, and the nature of knowledge itself. It's easy to look at a finished product, a weapon, a microchip, a pharmaceutical drug, and imagine that possessing that product means possessing the ability to replicate it. But as Factory 208's engineers discovered, the product is just the visible tip of an enormous iceberg. Beneath it lies a vast infrastructure of accumulated knowledge, refined processes, quality control systems, skilled workers, and industrial capabilities that took years or decades to develop. This is why reverse engineering, despite its apparent simplicity, often proves so challenging. You can disassemble a machine, measure every component, create perfect drawings, and still fail to replicate it because you haven't captured the tacit knowledge embedded in the original manufacturing process. The Chinese engineers' eventual success came not from perfect replication, but from understanding the M60 deeply enough that they could achieve its functional goals through alternative means suited to their own capabilities. This required them to move beyond copying to genuine engineering, solving problems creatively rather than simply following a blueprint. In the decades since, China's defense industries have continued to evolve. Modern Chinese weapons are increasingly original designs rather than copies, drawing on a mature industrial base and accumulated expertise. But the difficult lessons learned during projects like the Type 80 development remain relevant. The story serves as a reminder that technology is more than devices and designs. It's embedded in people, processes, and institutions. Acquiring technology isn't just about obtaining products or blueprints. It's about developing the entire ecosystem of knowledge and capability needed to create and sustain that technology. For Factory 208's engineers, the journey from confident optimism in 1976 to eventual success in 1983 was marked by frustration and failure and hard-won understanding. They set out to copy a machine gun and ended up learning something more valuable: how to think like engineers rather than copyists, how to solve problems rather than simply replicate solutions. That knowledge, purchased at the cost of 7 years and countless setbacks, would prove far more valuable than any weapon design could ever be.
The Type 80 machine gun fired its last rounds in military service decades ago, long since replaced by newer designs. But in the archives of Factory 208, gathering dust, are those 5 failed prototypes, each one a testament to failure, yes, but also to persistence. They remind us that sometimes the path to success is paved with broken bolts, warped barrels, and shattered assumptions, and that the most valuable lessons often come from what doesn't work.